continue to come to the class. So we are in a physical chemistry class. We hope to predict and interpret results of instrumental measurements, but we spend most of the time for math behind wavy nature of electron. We have almost, or we believe that we almost finished the electron in free space, and we sort of proved that it becomes more and more spread in space as time goes by. Hello, Nate, how are you? So I lied at least once more, or didn't fulfill the promise.
So all.
That's okay. That's okay. So we did mathematically predict how the width of the wave packet expands, but we did not prove that it will move on the straight line to the center, right? And this thing, this aspect, is possible to prove by the same method as we did, but it will not be as elegant. Oh, hello, Alison. Nice seeing you connected. So I suggest that we will use one more mathematical tools, which in total amount of intellectual efforts we'll spend about the same time. But instead of repeating the same procedure, we learn something new and then apply it in the actual solution to prove that it moves on the straight line, which will be much quicker. So this is the goal, and I will start talking about it maybe 20-15 minutes before the end, and it will be actual novelty. The rest of the time will be partitioned between making some administrative announcements and reviewing what we did in previous two lectures. So for administrative announcements, did everyone submit the work too? Did you? Or you brought it?
I have it right here, yeah.
Okay, yeah, let me collect it. And I do not have the full scale key, but I'm going to show maybe a little bit more on it. Excellent. I think everyone in the class took the accepted, absorbed, agreed, warrant, Fourier transform. And it may be not covered in other courses. If it is so, I'm a little bit proud of bringing this new thing. So briefly looking back into this homework, then reviewing what we accomplished before, and then we need to do two administrative things. Announce new homework, which I have forgotten to modify the date, and some of you may see Monday. I think Monday will be not right, only if you want double credit, but let's have the Wednesday, a week for homework, whatever will be the date. And I'll chat a little bit more what is there. And then another administrative thing is to sign up for the presentations on MATLAB. So it will be too much of squeezing our schedules if you do it this Friday, although you're ready by knowing all things. But it will be safer if you do it next Friday in like a week and a half. And then it's all basic things, but then you have time to make up your mind and slowly prepare. The 4-minute slides are quick to prepare, but just focusing and thinking about it ahead, it's better to do without rush. I'll show it as a slide, and also there is a link where you can just type in your votes on the Google Docs. Okay, so any suggestions, feedback, criticism about general plan or general organization of the course? No one objects. So I understand that there is a feeling that it is a little bit too much into the math, but it is not my fault. It's the fault of the subject. What should we do? Share screen. So the new material that you cover, I would call it time machine, but formally it's like Hermitian matrices. And you'll see it's much simpler than things that you have already went through. So here is the homework. So which I already watched you doing it successfully. So one identifies A and B and then practices full square, right? And after practicing full square, there is a term that travels outside of the integral, and then one identifies the variable that takes it as square root of pi because it is what we proved last time, Gaussian finite integral of the Gaussian function. So I've got this answer if you get slightly different factor like multiply or divide by 2, I don't care. It will be not against. If you find by errors, you'll get afraid. If I find little errors, I'll just close that. But in principle, if you got this momentum related variable in the denominator, this is main thing I'm looking for. So next homework, it has like 5 or 6 little sections, and they will be easier than those you have completed. So the first one, basically, you can find it in the notes. We did it. So it's just to refresh the concept of commutation because we will use it in the next couple of weeks. Another next one is just reproduce ways to predict future and scratch a couple of words how you interpret it. Then the question number 3 is something that I'm doing a bad practice. I'm weighing heavy things on your shoulders instead of explaining myself. But the justification is that you learn by doing. So it's quite simple concept that you can spend maybe 10-15 minutes in class, but if you do it yourself, you feel it by hand. So there was a question in the class when we introduced plane wave. Why do we place 1 over square root of n in front of? I think several aspects. So all wave functions must be normalized. If they do not come naturally normalized through procedure of solution, humans must to make an effort to normalize it. Why it is needed? Because the main goal of the wave function is to help predicting outcomes of measurements, right? And in order to predict outcomes of measurements, one needs to find expectation values of operators. And here is one of the examples of this position. So if the wave function is multiplied by some arbitrary number, then the result will be multiplied by arbitrary number and will be not trustable. But if you make sure that the wave function is, so to say, normalized, which means without any operator here, integral of the wave function will be 1, then the result will have relation to reality. And the procedure is simple. You take wave function star by itself, integrate, and then take the result. If it is not 1, you take square root and divide everything by the square root, right? So find n for this Gaussian function. And then plug it in and find expectation value, which you should get this x naught. If you do not get x naught, it means you didn't normalize it correctly. It's kind of, you can check yourself if you're doing that. If you feel a little nervous, you just open German money or Wikipedia for Gauss distribution. Normalization will be whatever you find it there. So it's famous equations like 1 over square root, and then there will be width parameter and pi. But you can find it yourself and feel proud. Okay. This is also copy paste basically from the notes. So repeat what we practiced together last time. Like how do you interpret the product of these two uncertainties in previous. And number 5. There is number 6, which is not counted. If you do it, you will get more than 100%. And you see it at the bottom in the slides. But number 5 is kind of, I wouldn't say complicated. It just makes us to do a sharp turn in the style of our thinking. So let me do a little interview about your experience in the differential equations, which I believe more than half of the class already took. So about a week ago, we discussed about general and particular solutions, right? So general are useless, particular are helpful for scientists and engineers. So how do we find particular solutions? Please.
Either initial conditions or depending on the, like there are different layouts that correspond to different things. Like if you have a
You're telling an important thing. I think you need a microphone. Yeah, please keep going. It's helpful for everyone.
either initial conditions or you solve for constants in the general solution by using a different, like standardized equation.
Okay, everything is correct, but let's look for anyone wants to help more. I'm looking for one keyword that starts with letter B and is already exposed in my Outlook and Scratch.
Boundary.
Excellent.
Boundary.
Yes. Please show your, if you agree, think thumb up, disagree, thumb down, or you don't care, or you need more explanation. Okay. So, Adam, let me take it from you. What do you think about boundaries? Are they good or bad?
Pretty good.
Okay. Do boundaries ever help you to solve differential equations?
That's suppose.
Okay. Yeah, thank you. Sybil, tell your success story how boundaries help you to solve differential equations.
I don't want to do differential equations.
Sorry.
That's a both my
Better answer for the interview. What are differential equations?
Exactly.
Joe, anything about boundary equations, boundary conditions?
They kind of help set like initial and final like parameters for what you need to solve.
Excellent. So do you like the word of Joe? Initial and final parameter, right? Make sense? Anyone wants to add a little to the discussion or? Okay, yeah, I think it's yeah, many thanks. Adam, Joe, Wyatt, Sybil. Next time I'll ask everyone. No, it's a really discussion. So here is an example of general solution, right? And by selecting constants, there are 4 constants: A, B, alpha, beta. We can match boundary conditions. So boundary conditions will be that this function, function of x must have value 0 if x equals 0 and must be 0 if x equals L. Right? So I can give an immediate example of solution. If I discard cosine, if I put b equals 0, and if I put alpha equals pi, and then take any a, the sign starts at 0 at 0 and will be 0 at the half period. But I'm asking you to be a little more systematic and scientific and find what if there are different alphas. Why this question is popping up, and why I'm asking you to do it instead of me practicing. Do not worry, I will do it on the blackboard after you try. Do any of you ever thought about teaching career, or you all are thinking about industries and research? Okay, anyone looking for industry? Or anyone looking for research? Okay. Anyone looking for teaching? Okay. So why then you are my primary audience in the next 3 sentences. If course of this content is offered at earlier, not in the 3rd year of undergrad, but like 1st or 2nd, or at high school, if one teaches it not at the major research universities, but at small schools, everything is squeezed. Most of details are wiped off. But this problem of the boundary conditions for this function is the core of the course. So it's one of the simplest example manifesting all concepts of quantum theory for physical chemistry. So if you deal with so-called problem of particle in the box, and in real life it corresponds to oligomers of conjugated polymers and quantum dots. By solving this equation, one will show by giving this answer, you will find eigenstates of the total energy operator for the wave function that is constrained inside the box. And by teaching similar course, if life makes you to do so, this problem will be unavoidable. So it is no matter is it complicated or shortened, it is there. Enough as a motivation. Okay, and I think I am kind of wasting time. Okay, so please try to do it by coming Wednesday, and if you want to create a safety cushion for double credit, you can do it by Monday. Meaning I will not provide any keys on Monday, and on Wednesday I will provide keys. So it's so here is the list of subjects. I think the number of attendees is 9, right? So 6 in class and 6 online. And if you follow the link, browser, you will see the subject. So basically there are functions, work with matrices, visualization, and 3 things about programming. So please select whatever you find interesting and appropriate, and maybe make 2 choices, so that either if everyone, like, I would definitely select movies for myself if I would be in the class, but maybe it's someone else who wants to do it. So please make first and second choice, and I will meditate over it and look over it in calm, silent situation, and then let you know the final schedule. But your opinions are primary criteria for selection. Okay, yeah, thank you for making choices, and I'll go forward with the class. So I'm going to very quickly jump over the subject that we did on the previous two lectures. I believe we all agreed on everything. So it's maybe a little bit less ugly and scratching and more type equations, but there will be nothing in between. You already absorbed all concepts. So this is your homework. This is the way how we practice third way to predict future. And here is the little dictionary how we can do it. So the problem of predicting future of this Gaussian wave packet is just to take the integral where we practice this little conversion. We identify the table integral of area under Gaussian shape, which is square root of 5, and find answer in terms of this constants A and B. And when we plug them back carefully, we observed that the constant A, which includes time increment, is coming into the denominator. And the answer will look this way. Normalization constant, which we can also find, but here position squared, and then the denominator. This is not a comfortable function to work with, and wave function is not an observable in any experiment. So we, for intuitive human interpretation, we need a probability distribution, which is wave function square or wave function conjugated times wave function. So if we take the conjugation, I need to focus on this. Then one just flip sign for the time. If we practice it carefully, so it will be product of exponentials. Once it will be plus I, another time minus I. The powers of exponentials get together, right? And then one needs to practice the middle school algebra for bringing things to the common denominator, right? And the common denominator will be product of these two denominators, which will be like sigma naught plus I, sigma naught minus I. And on the denominator, you just add this things. By adding together stuff with plus and minus I, they cancel, and you'll get just the sigma naught with. And in the denominator, by practicing this product of sum and difference, you will get multiplication of I times minus I, and you will get rid of the imaginary component. Everything will be real. It will be sigma naught squared over 4 minus this stuff squared. Which will be sigma squared over 4 plus the stuff multiplied by time squared with some factors. Then this thing from the denominator can be extracted and analyzed as a width of the wave packet as uncertainty to find position of the vector. So I think it is one of the questions in the homework. How does it changes over time? So instead of it starts at a certain level and then it keeps growing. And the product, since the uncertainty of momentum is not changing, the product will also grow. So if we take arbitrary time, then product of uncertainties will be equal or bigger than this A bar square over 2, because the additional term is always growing. And this statement in the red books is mentioned in textbooks and in Wikipedia and called an uncertainty relation. So the one interpretation is that one cannot simultaneously measure position conjugated variables such as position and momentum with arbitrary precision. Uncertainty relation. Here's the class of 2021. Class of 2021. Here's uncertainty relation. Okay. So, actual lecture number 12. We're going to arrive to this equation, where the first one is regular time differential equation, right? And the second one is a result of putting a little cross or dagger applying to each component of this equation. If you don't care about real world, real nature, you just mathematically. So this Hermitian conjugation means that we transpose matrices if we or vectors if we see any, and we do a complex conjugation if we see any imaginary units. So everywhere where we had psi, we have psi star. Any were extra credit for finding errors. There is multiple errors, so multiple chances for the extra credits. Anything missed on this equation, I need to read it from the recording because or at least make it unlisted and not public. So anything is missed in well, like usually the first equation is not new for you. Is anything is missing there? You all can catch me. I have no doubts. Just look carefully or close your eyes and remember how the time differential equation should look like and tell what is missing. I think it's a very good pedagogical exercise, but it's not intentional. It's mainly learn on my mistakes.
So they're like const.
Okay. Yes. So Nate, last one. So one constant. Is anything else is missing?
Imaginary number.
Should it be plus or minus?
Minus.
Okay. I heard several voices, but the the extra credit goes to louder voice. So for H, it went to the Nate. For I, it goes to Wyatt, and for minus, it goes to Joe. And I've heard voices of Sibel and Adam. Maybe they should also should get points. Yeah, many thanks. And if we do it, if we do conjugation, it should be swap the same. Yes, I over each one. Right? Yeah, thank you for catching the error. So we swap. We put star. We swap sign in front of imaginary unit, and look here. We had Hamiltonian times wave function. Wave function times Hamiltonian. It's surprising. Will you accept it naturally, or will you protest, or just ask why it is this way? So let's. I probably would hesitate to raise hand until I do not understand it, but I would, if I would sit in the class and make notes, I would write to myself, I do not believe it. I need to figure it out. It's either a mistake or something I do not know. Maybe some of you feeling similar way. So so there is a little surprise of swapping the order, and basically the remaining 20 minutes I needed just to digest this equation and agree that the way we see it here is legitimate. The motivation and benefit of this equation, why are we doing it? Why do we need to spend time on more concepts? Because it's quite natural if we all get tired of concepts and abstract mathematical equations. So by learning this concept, we will spend some time learning them, but then after we get them, we will be able to predict in a couple of lines that the center of the wave packet moves on a straight line. And it is not the only motivation. Later on, the things that we are learning right now will help in other problems as well. This set of concepts, the area that we are touching right now, will be more closer related to finding outcomes of experiments, to find expectation values and results of measurements. So I never was able to memorize what are the numbers of postulates. You probably are much more educated in this after you did presentations, but it's like number 5. That if one knows wave function, if one knows operator corresponding to observable, one can find expectation value as a result of series of experiments. Like single experiment is always ideal value, but if it is multiple measurements, it will be expectation value, right? So look here. On the right, we do have normal, regular wave function without conjugation. On the left, we do have wave function with conjugation. We do know how to predict future for regular wave function. And if you find it as an equation, we can always convert it to conjugated wave function just by putting a sign in front of the any imaginary unit you find. But what if the problem is so complicated we cannot write equation? It cannot be solved by pen and paper. Where do I flip the sign of imaginary unit if it is just set of numbers? What if the set of numbers is changing? I may try to flip numbers in all complex values, but maybe there is a more elegant way to approach it. Maybe instead of finding regular wave function and then flipping to conjugated, one instead can find equation of motion for the conjugated wave function. Okay. And this is the way how we look at this thing. So we want to practice expectation value, and we want to have a way to predict conjugated wave function, so to say, independent. So star means flip sign in front of imaginary unit. Transpose means keep diagonal the same but flip off diagonal, right? And if one makes this little dagger or cross sign, it means doing conjugation and transposing simultaneously. This is not a way to torture young people. It's just made by humans for humans, and just by designing the theory, one found that this procedure of transposing comes into the play. So if one has the imaginary matrix and one practice transposing, then one is picking the diagonal elements, flipping the off diagonal, and swapping the sign in front of any imaginary unit. So how do we practice this transposing procedure to the vectors? So if the matrix keeps diagonal elements and flips off diagonal, what happens to the vector if you transpose it? This is something whoever will select work with matrices can cover in the presentation in the written stuff. And in MATLAB, we get it just by putting apostrophe. So if you have a row vector and put apostrophe after it, what happens to it? Column, right? What do you have a column vector and put apostrophe? Yeah, so it swaps row and column from row to column vector. So it is here. So, this symbol is also often referred to in textbooks as Hermitian conjugate. So it's just based on the mathematician who practiced it many times. So do not fear this word. I was one of my impressions of first time taking quantum theory that come on, they're bombarding me with names without any meaning, like Hamiltonian or Hermitian, both starts with H. What's the difference? So Hamiltonian is energy, Hermitian is dealing with transposing of matrices. And now let's apply the thing to a product of matrix by column vector. So if we apply this Hermitian conjugation to a product of matrix by vector, we are getting swap of the order. So conjugated vector by transposed matrix. And we will not do it, but one can prove it. So if we accept all rules of row by column matrix multiplication, if you plug in certain values, then one will find out that the result of this multiplication will be the same. But we try to convince at least myself. So matrix by column vector, row by column will generate a column vector as a result, right? And applying this transposition, it will be the result will be a row vector. Practicing row by column for this construction. Row by column, if you generate a new row vector. And we do not have any operation here. So this will be row vector as well. Okay? So it's not a proof, but at least it helps us to be a little bit more comfortable with this notation. Does it make sense? Completely no sense? More comments? Or? Completely no sense? Question?
More comment.
More comments, okay. Would you agree that matrix by column vector will be column vector? Would you agree that transposing the resulting column vector will be row vector? Okay. Now, would you agree that multiplying a row vector by matrix will be another row vector? Or you're not sure? Okay, let's do this little exercise. Okay, I'll use it's right here. So right? And this will be element here. Now, if I do it row by column for the second column, it will be next element, if you have the same coordinate as this black line in the matrix. So here it will be x times d plus y times d. And it will be two independent elements for the column, for the row vector. Okay. So we are getting the row vector here because of conjugation, and we have a row vector here just by nature of row by column rule of matrix multiplication. And in order to have this homogeneity of the style of data of row vectors on vector right, here we need to swap the order and flip the vector right away. So naturally, so it is kind of clear for matrices, but can we do the same thing for arbitrary operators? If we do not know yet the matrix form of our operator, or what will be differential operator for the stuff we are, for energy that we are discussing, we still can inherit this little experiment on linear algebra from the previous slide and tell if we put Hermitian conjugation here, then the result should swap the order of the wave function and the operator, and here we will have the conjugation. So we kind of projecting our experience from linear algebra to more general way of operators. So in order to have the identity of style, same style data, we need to swap the order of the wave function and the operator. Absolutely yes, absolutely no. More comments? Okay. I already told the best I can. I'll try to once again, because this stuff was irritating me at my time when I was taking this class. It looks a little unnatural. If we always, we are not always thinking of wave function as a vector, but if you would think of the wave function as a vector, that can be either row or column, then it will become natural. Right? So in order to accept this notation, we should maybe wrap our mind around wave function and just tell to ourselves, wave function is always a vector. But if it is a function, how can we think of function as a vector? We can think the function is just a set of numbers that are arranged as a vector, and the numbers are spaced very densely. And then this vector can be placed as a column or as a row. Does it make you to feel better? Okay. Now I'm very happy. I'm very happy for you accepting this idea. In my time, no one explained it to me. It was assumed like self-evident, like nature of selection. You either understand it yourself or you are not passing yourself. Now let's look on this from the other side. If so, everyone accepted that this notation has right to live, and we accepted it by appealing to linear algebra and vectors. Now let's look on it from the point of differential operators, because energy operator Hamiltonian is always just set of derivatives. And by everything we were taught in calculus, by all our experience, we always had differential operators being from the left in respect to the function. So we always were thinking that differential operators act from left to the right. But here, we know the result is convolution of this matrix or this operator and this wave function. But there is nothing to the right from the operators. So if you say A, you need to say B. And natural continuation of us accepting this identity will be to accept the idea that in this transposed modification, the differential operator acts from right to the left. This is very hard to accept. This is unnatural. But it is what we need to do in physical chemistry and quantum theory. So here, the differential operator acts from right to the left. I am not asking, are you agree or disagree? If the normal human cannot accept it. Let's just memorize that it is a convention. So if we do Hermitian conjugation of the operator acting on the wave function, then we need to accept that operator acts from right to the left. One more thing. That I'm skipping derivations, but by good luck, energy operator doesn't change upon Hermitian conjugation. So, for example, well, I'm not going to prove and give arguments, but if you cast energy operator, we never saw imaginary units there, like second derivative of position for kinetic energy and then just function for potential. We didn't have any potentials. But anything we do to model energy, especially if you convert it into matrix form, will be always symmetric and will be always real. And it is a statement that is skipped away from this course. Energy operator is always Hermitian. Therefore, with this conjugation symbol or without, it will be the same. It will be the same H symbol. So it will be the same Hamiltonian, but now it acts from left to the right. From right to the left. Opposite way. Okay. So matrix. Form, conjugation, form by matrix. Rho by matrix. And if we practice it in application to the Schrödinger equation, independent Schrödinger equation, if we consider the Schrödinger equation as form, matrix form, upon doing conjugation, we get rho matrix. If you do matrices, it just swaps the order. If you do differential operators, we need to say that the operator acts from right to the left. So it's basically the final thing that we've got. If we convert this stuff into the evolution operator, you'll see that evolution operator can be cast in the same way as we did before, even with -i, but then one needs to change time t to the time minus t. So in some sense, propagating this stuff by this equation will correspond to moving backwards in time. It doesn't mean that we have actual time machine, but mathematically, this conjugation means we're propagating backwards in time. Done? Thank you for being patient and tolerating me and the subject. Meeting is done. Everyone is welcome to disconnect. I look forward to see you at 5 in the QBD 132 for the. I'll stay here to answer any questions, but if you need to go, please feel free to depart to your next appointment. Josh, Allison, May, do you have any questions? Do you allow me to disconnect or you want me to stay and answering? More questions one. More questions two. More questions three. Josh, Allison, May, I'm going to disconnect.